So, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 20 and the topic is symmetries. Symmetries play a very important role in physics in general and in particle physics in particular. It helped physicists to discover so many new laws of nature. It is often said that physics is the study of symmetries. In today's lecture, we will first give the definition of a symmetry, and then we'll give its different properties, and then we'll give its importance and examples in particle physics. So let's start with the definition of a symmetry. By symmetry we mean that an operation which is performed on some system that leaves it invariant. So what do we mean by this definition is that whenever we have some system and on that system we perform any kind of operation, consider the system to be a sphere, and if we perform on it the operation of rotation, then what happens that after certain rotation, for example, after rotation of 30 degrees, if the sphere is same from all directions and its shape will not change, and we will not be able to differentiate the shape of sphere before and after rotation. So we say that this operation of rotation is a symmetry operation because after performing the rotation, the shape of the sphere was not changed. So this is one of the simple examples from where you can see that in symmetry, whenever we do some operation and with respect to that operation, the system is not changed. That is, it is left invariant, and we are not able to differentiate between initial configuration, that is before the operation of a operation performed on that system, and the final configuration, that is after the operation is performed. If we cannot differentiate between these two configurations of the system, we say that this operation, this particular operation, is a symmetry operation. And we often name that symmetry with that operation. For example, rotational symmetry would mean to rotate an object, and after that rotation an object is not changed, then we say that this is a rotational symmetry. We will see many examples of them, but before that we go to the importance of a symmetry, that why this symmetry operation is so important. I will explain this with an example of this function. If you look at the graph of this sum function, we don't know what the function is, but we have just plotted it. So on x-axis you can see with respect to f of x we have plotted, and you can see different peaks, and from this plot you immediately can know that it is an odd function. If you multiply f of x with minus f of x, then the plot will not change. So this oddness is actually its symmetry operation. So here you see that if I change f of x with minus f of x, this plot on the previous slide is not changed. It will remain same because this plot over here is actually minus of this plot. So therefore, if these are both combined, if you plot f of x or minus of f of x, this graph is the same. So we say that changing f of x with minus f of x is the symmetry operation. So this symmetry operation is there, but the important thing is that without knowing the form of the function, we can deduce many of the properties of this function with the help of this symmetry. For example, we know that this is an odd function. So for an odd function, we know that if f of minus x raised to power some even number is equal to this thing. So although we don't know the form of the function, but we know that this function shall obey this property because of the symmetry there. And also another, under the integral under some limits, this f of x dx should go to 0, because plus and minus parts will cancel each other. And similarly, if we take the derivative at some points, they are equal at plus 2 and minus 2, for example. And there is another, for example, if we integrated enter a certain limit, the square of it, then it is equal to the integral on the right side. So all these properties are deducible from the symmetry of that function. So you see that the symmetry is a very powerful tool. This is one of the examples where you can see that how symmetry can tell us so many things without actually knowing the exact form of this function, that it is a sine function, but we didn't know. Just looking at the plot and knowing that there is some kind of symmetry involved, we can deduce so many properties. Okay, this was about the importance of the symmetry. Now we go towards a very important and famous theorem regarding the symmetries that was given by a German physicist, Noether, and it is called Noether theorem, and it is the law of nature, that to every symmetry there is a corresponding conservation law in the nature. So whenever there will be a symmetry, in either it is an equation or it is in the system, there will be a corresponding conservation law for that symmetry. So for example, we had a rotational symmetry, then there must be some physical quantity which it conserves. Okay, now we go and give you some simple examples of this Noether theorem. For example, first of the symmetry we see in our nature is translation in time. What do we mean by translation in time? Is that the laws of nature do not change with time. For example, Newton law was valid yesterday, and Newton law is valid today, and Newton law is also will be valid tomorrow. Or you can say Newton law is valid when the universe was created, and it will remain valid till the end of the universe if it is there. So we see that when we translate in time, that is when time is changing, time is passing, then there is a symmetry in the laws of nature. And this is not only the Newton law, all other laws, for example, Coulomb's law or gravitational laws or any other law which is proved to be law of the nature, it is in when we move in time, when we translate in time, when time is changing. So this is the symmetry operation, that change of time is a symmetry operation. So there must be something which is conserved, because law of nature is not changing because of this symmetry operation, translation in time. Then there, according to the Noether theorem, there must be connected to this symmetry, there must be something which is conserved, and you can see over here that this is energy. So energy is conserved because of the translation in time symmetry. If there was no symmetry in regarding the translation in time, when we moved in time, or timing passing and laws of nature were changing, then we would have not got the energy conservation. So law of energy conservation comes from the symmetry of laws of nature under the translation in time. The second example is the translation in space. So when we move from one point to another point, for example, in the universe, if we move from one point to another point, again the laws of nature will not change. For example, the Newton law is if it is valid on the Earth, and if it is also valid on the Jupiter. So if you move from one point to another point in the space, the Newton law or the Coulomb's law or any other law of nature will not change, it will remain the same. So therefore there must be a symmetry connected to this because of this theorem. And the symmetry which is connected to the conservation, which quantity which is conserved under the translation in space, is momentum. So there is a law of conservation of momentum because of the translation in space. Okay. And we already talked about the rotational symmetry, and we said that whenever the system is invariant under the rotation, whether it is a continuous rotation or it is a discrete rotation, but if the system is invariant, that is, it is not changing when the rotation is applied, then we say that there is a rotational symmetry. And when there is a rotational symmetry, then the corresponding physical quantity which is conserved under this rotational symmetry is angular momentum. So angular momentum is conserved quantity, and it is connected to the symmetry called rotational symmetry. So these were very intuitive or famous type of symmetries and symmetry operations and their conservations. But there is one another, and it is called gauge transformation. What do we mean by gauge transformation? In particle physics or in electrodynamics, you know that we have electric field, and electric field strength is defined by gradient of some potential, let's say call it V. And if we add some function to it under this derivative, then this constant function, then we know that this derivative of the constant function is 0. So although we have changed the potential, you see over here we have changed the potential, but electric field is not changed, because the derivative of this constant will go away and we will be left with the same electric field. It means for many different potentials, so it is symmetric. So this changing the potential is a symmetry operation on the electric field, because when we change the potential, it leaves invariant electric field. Such kind of change in potential is called gauge transformation. And this gauge transformation has a connected conserved quantity which is called charge. So charge conservation comes from the gauge transformation. So all in all, I gave you 4 examples of the symmetries and their corresponding conserved quantities. For example, translation in time was energy, translation in space was momentum, rotation was angular momentum, and the gauge transformation, as I have explained here, gives rise to the conservation of charge. Okay, so that was a very important theorem about the symmetries, which connects symmetry operation to the conservation law. So it's time to move towards a particular example and try to construct the symmetries and see how some object remains invariant under some operation. So I will give you the very simple example of equilateral triangle, and will try to construct the symmetries, all symmetries of it, and then after constructing all these symmetries operations, we will be able to see that there is a group structure in these symmetry operations. And group is a mathematical theory for or mathematical structure for analyzing or studying symmetries. So therefore it is important to connect now these symmetries to groups, and this we will do with the help of discrete symmetries found in equilateral triangle. Okay, so this is an equilateral triangle, and by equilateral triangle we mean that all its sides are equal, that is side AB is equal to side BC and AC, and we have also drawn a line which is going through the vertex A and side BC, and we call this a line A. And we can also have another line on going from the B vertex, and we can have a third line going through the C vertex, let's say call it a C. These 3 lines will actually help us to form some symmetry operations. So looking at this equilateral triangle, now it is easy to find out that there are some symmetry operations which we perform on this equilateral triangle, and the shape of this equilateral triangle will not change. For example, the first one is rotations. So there are certain rotations under which this equilateral triangle shape is not changed. For example, the first one is the clockwise rotation by 120 degree. So if you rotate the equilateral triangle by 120 degree, then what happens if you rotate this by 120 degree, then this C will go to the A will go to the B, and B will go to the C. But since these are just the labels, these are not exact points, these are just the label, and then you can relabel again and call this C A, B, C, and this one will be not able to differentiate between this initial configuration and final configuration of this equilateral triangle. Therefore, we say that this rotating by 120 degree is a symmetry operation, and let's call it R plus. So this is R plus and it is a symmetry operation. Similarly, if we do the counterclockwise rotation by 120 degree, again, I mean, if you rotate it in this way or if you rotate it in this way, in both cases the shape of the equilateral triangle will not change. Therefore, we call it a counterclockwise rotation by 120 degree, and we name this symmetry operation R minus because the shape of the equilateral triangle is invariant under counterclockwise rotation by 120 degree. So R plus and R minus. You might be thinking that what if we rotate by 240 degree, but if you rotate by 240 degree, the equilateral triangle is still invariant under 240 degree, but 240 degree rotation is equal to the counterclockwise 120 degree. So it is not unique, or it is not independent. Symmetry operations are always independent. If same thing can be achieved by two symmetry operations, then we consider it one because they are equal. So therefore, I have not mentioned rotation by 240 degrees. So because it is equivalent to the counterclockwise rotation by 120 degree. So we have now these two symmetry operations by rotation, that is R plus and R minus. You can think for yourself that why not the other rotation by other angles, for example 130 degree or 90 degree or 45 degree is not a symmetry operation, because these are not symmetry operations because they do not bring the equilateral triangle to its initial configuration. Okay, then there are other symmetry operations involved in here as well. For example, flips, for which we constructed these lines through the vertices, and the first of them is flipping about axis A. If we flip, which mean just by flipping it around axis A, will not change the equilateral triangle. For example, you can look at over here. If I flip it over here, this C will go to the B, and B will go to the C, and A will remain at its point. But then I can relabel B to the C and C to the B and B to the C, and the initial configuration is not different than the final configuration. And so the flip around axis A is not is a symmetry operation. Okay, so we call this symmetry operation RA. So flipping about axis A is a symmetry operation RA. But this is not the only symmetry operation by getting flips. You can already guess that we can have flipping about axis B, and this is also a symmetry operation. We call it RB. And the third one about flipping is flipping about axis C, and we call it RC. So these are the three flips. So we got two rotations and three flips. So this is first flip, second flip, and third flip, and these three flips are the symmetry operations, and also the two rotations are the symmetry operation. And there is another one, looks trivial, but an important one is identity. What if we do nothing? It is also a symmetry operation if we do nothing. Now, doing nothing is a symmetry operation, and it does not change the shape of the equilateral triangle, although it seems it is trivial, but it is required in the construction of the group structure for these symmetry operations, which we are moving towards now. So after constructing all these symmetry operations for equilateral triangle, it is important to check some of their properties. The first of the properties is a closure property. By closure property, we mean that if we have two symmetry operations, for example Rj, so Rj could be R plus, R minus, Ra, Rb, Rc. It could be, for example, this first R could be the flip or could be any rotation, but it is a symmetry operation. And if I perform this symmetry operation on on this equilateral triangle, and then after performing this, I perform another operation. For example, I performed Ra, and for example, I first perform Ra, and later I perform, let's say, R plus. And if I do this, I will get something here, some Ri, which is also a symmetry operation. For example, I could get Rb over here, for example. You can check it for yourself. If this is so, then we say that the every two operations we perform on this equilateral triangle, the symmetry operations, this is equal to another symmetry operation. We call this property of this symmetry operation as a closure property. So this is a closure property for the symmetry operations. We will see that these properties will help us define groups, but let's check one by one all of them. The second property is identity. As I have already mentioned, that identity is required for the definition of the group. That's why, although it seems trivial, but it's not trivial, and it's important for making these all symmetry operations as a group. So it's very easy. So if you have a symmetry operation, first you perform a symmetry operation and then you do nothing, or you first do nothing and then perform a symmetry operation, this is equal to that symmetry operation. Since it's an identity, so it will not change Ri from either side, doing first Ri or doing last Ri, it will not change it. Therefore we say that this is by definition is identity, because it is not changing the effect of this symmetry. So we know that all symmetry operations, either these are flips or they are rotations, they obey this symmetry, this identity structure over there. When we multiply them with the identity, these operations are not changed. Now we move towards the third property, which is called inverse. So what do we mean by inverse? By inverse we mean, if we have some symmetry operation, for example a flip or a rotation, there must be some another operation which cancels it. For example, if I do the rotation, if I do the clockwise rotation, and then I do for example some flip, let's say RB, and this is R plus, so maybe that they cancel each other and they come equal to I. So Ri minus 1 Ri, or Ri multiplied by Ri minus 1, this gives us an identity that somehow they cancel the effect of each other. So for every symmetry operation, there must be another operation which is the inverse of each other. This is the property. You can check for all the symmetry operations this property, that there is a symmetry operation involved, which is the inverse of this original symmetry operation. Okay, so this was the third property, and now fourth and the last one is called associative. So what do we mean by associativity? By associativity we mean if we have three operations performing on this equilateral triangle in a row. For example, first I do Rk, then I do Rj, and after them I do Ri. These are for example, I do a flip, I do a rotation, and I do flip again or rotation again. And if I change the order of them, for example, I decide not to do Rk first and Rj second and Ri third, but I do Rj first and then do Ri and lastly do Rk, because this parenthesis is telling us which two operation shall be done first. So on the left side we have done first Rk and Rj and then Ri. On the right side we have done Rj and Ri and then Rk. So in either case the result will be the same, and this property is called associative property of the symmetry operations. Okay, so we have completed all the four properties, although I have not given you the exact check, but this is left as an exercise that you go to the symmetry operations and try to construct a table. It is called a multiplication table. That will be an exercise that you construct the multiplication table for all these symmetry operations. So multiplication table is constructed in this way, that here you write the operation and here you write all the symmetry operation, for example R plus, R minus, R A, R B and so on, and then you have these rows R plus again and R minus, R A, R B and so on, And then what you do, that you first perform R plus and then R plus and write out what comes over here, and then similarly R minus R plus and write out, and in this way you complete this whole multiplication table, and then you will be able to deduce that which one is the inverse of symmetry operation and which one is the identity and which one is which. So this is gives us the in discrete symmetries case, this gives us all the multiplication table or all the symmetry operations, the combination what we get from the combination of two symmetry operation, this table will readily tell you. So your exercise would be to construct this symmetry multiplication table. Okay, so once we have completed the analysis of the symmetry operations, we go towards groups, and as I have already mentioned that all four properties are defining properties of the groups. So any symmetry operations which obey these four properties, we call them to form a group. And group is the systematic study of the symmetries in the nature. So in nature we study groups, and also in particle physics we study symmetries with the help of groups. And you will see that for all kinds of forces we have, there will be a symmetry because these are the gauge theories. So there will be a symmetry group for all forces. Actually I mentioned them over here. So in symmetry in particle physics is, for example, okay, so there is an important thing that matrices also have symmetry. For example, all unitary matrices of order n have this unitarity, and this is the matrices in the group, and they form this group UN. And then there is a special unitary matrices, they also form a group, and they are those matrices which have unitarity with the determinant 1. And then orthogonal group, and then the special orthogonal group. So these are very important groups, and these are the symmetry groups, because all the operations involved here form a group structure. And we will see that in particle physics in detail in coming lectures, that how these groups are applied. And we will also see that all the four forces are actually the gauge theories, and they have a gauge group for them. For example, electrodynamics has a gauge group U1, and weak force has a gauge group SU2, and a strong force has a gauge group SU3. So I will tell you in future lectures that what do we mean by these gauge groups, and how these gauge groups or the symmetry groups explain to us the different forces in the particle physics. Okay, so in today's lecture we learned about the symmetry, the definition of the symmetry, and we also learned that it's a very powerful tool. You can already deduce so many things from the symmetry, knowing just the symmetry without a lot of information available. That's why it was very popular and a tool in particle physics, because people applied the gauge symmetries and derived and discovered so many theories and so many laws of nature. And then I gave you a concrete example of the symmetries of the equilateral triangle, and then we have seen that the symmetry operations of the equilateral triangle form a group, and group theory is actually a systematic study of symmetries, and we apply symmetries in particle physics with the help of group theory. With this, I thank you all.